If you want, you put one of your slides. No, you can. It's fine. Yeah, I'll just click it.
Good luck. The first time you presented to me.
Yeah. I had a different version, and you would hear something. I had like yesterday. I had like 2 hours to like. I was.
Usually you.
Yeah. Yeah, thanks. Yeah.
Nice to see you here. Better, but yeah, it wasn't mild, like no fever or anything. But don't want anyone to also have no mild. It was inconvenient.
Oh,
yeah.
sure. You knew it's fine. You know, and then, but if it's like 2-3 minutes more, it's no problem, right? Take it easy then, so everyone understands.
Those are the names are really.
Yeah, of course, yes. Yeah.
Sophie said she would do right?
Yes, because you got stranded.
Yeah,
in
from Madrid. Yeah.
Yes.
But I'm leaving on Friday, so I would like to meet her.
Yeah, sure. I mean, if everything goes right, she has a flight on Friday.
Yeah, okay. She's been applying for yeah.
Another week. More or less, yeah. But I asked.
Our things for you.
Sorry, I arrived at 10 morning. That's why I was in the office. I was like,
Sorry, okay.
I heard there was a lot of silence. I was like, very good, yeah, busy.
Yeah.
But yeah, I don't travel so much. I had
Yeah,
peak
yeah, I'm
the
happy.
conferences I can attend. So.
Yes. And I'm checking.
Yeah, it's like it's difficult to have the picture. And then
Yeah, but then I was like,
different MP that
And here I'm checking. And every 2 weeks they.
congratulations. Sorry? Congratulations for that.
No, tu puoi.
your times are not my.
My work. Inizia così, eh?
想锻炼来着。
Ti racconterò. No, I think the best finally. There's so many people in the best.
Ma senti,
You're actually trying. Mara, Johan, you, me.
is
Yes.
Okay. Thank you all for making it here. A bit shorter lunch break than there will be during this workshop. So we have one presentation now from William about Euclid. So I'm sure many of you will be curious to know. And then we will have some time to rearrange, sit, and the idea is to have this speed collaboration. Yet another chance to talk to a few more people that you don't know. Okay. So, hi everyone, my name is William Rosta.
Sorry to interrupt, can you hear me?
Yes.
Could you please turn the video on of the room?
I am not sure there is, I mean, the computer we are using to do Zoom.
maybe this, Andrea.
Is it this? It's on now. The camera here.
I mean, that is.
Yes, thank you. That's the one I mean.
Okay. Thank you. Okay, well, so again, I'm William Ross. I'm a third-year PhD student. I work at MPE just across the street. And since Antonis was talking about future surveys that might open up some new doors to AGN identification, I'll give you a quick rundown of what we're investigating with Euclid at the moment. So with the new data coming in. So in case you're wondering, Q1 is quick release 1. Euclid nomenclature, and it's I'll explain in a second, but it's basically like the first internal release, and then next week public of the first observations that we're doing with Euclid. Okay, so I'm heading SP003 with some other people, which is one of the projects that will be published next week, and so because it's not yet public, I have to put preliminary results on all of the slides, basically. So if you want to take a picture, feel free, but please make sure that you ensure one of these preliminary results, because if you don't and it gets public, I'm going to be screwed. So just so you know. Okay. As for SP003, just to give you a quick breakdown of what we're doing, basically the entire goal of the project is to identify all of the AGN that we see in Q1, to do the scientific exploitation of those. How do we do that? We use X-ray information. So we start from selected, detected X-ray point sources. I say point sources because at this point we don't know that they're AGN yet, because we don't put any sort of cuts on any potentially spurious detections in the parent sample. We do this because, as known, with X-rays we have very high nuclear to host emission ratios, so we get very pure samples. Perhaps not maybe some other wavelengths, but sufficiently, of course. And then the challenges which come with this project are also primarily driven by some of the caveats of the X-ray surveys, such as, for example, the positional uncertainty. In Euclid, we have the high source density that we're dealing with, and then lastly, the auxiliary data not being homogeneous. I'll go through all of these individually, so no need to worry. But let's start with the first. So I mentioned the positional uncertainty, so let's get right into it. So on the left-hand side, what I'm showing is the X-ray flux as a function of the positional uncertainty in these X-ray surveys. And so what you can see is there is let's say, divide between the pointed observations or the pencil beam surveys, in this case 4XMM, DR14 in this case in purple, and Chandra source catalog 2.0 in orange, where you see that you get pretty good positional uncertainties, maybe on the order of like 2-3 arc seconds, but obviously at the cost that you're only looking at a small field of sky. Whereas then if you go to Rosita DR1, which is sort of this banana-shaped gray distribution, you can see that even though it might extend up to 10 arc seconds or so, we're getting all sky observations, so we're more likely to cover also those maybe rare bright objects that you otherwise wouldn't see if you have a pointed observation. So as always, there's a bit of a trade-off going on. Now this is one side so like what comes in with the X-rays when we're trying to identify these counterparts to these X-ray surveys in Euclid Q1, and then Euclid on the other side, so the plot with this commutative histogram, where you can see that because we have high source densities on the order of 500,000 sources per square degrees, or search radii, which is sort of given on the x-axis in order of arc seconds, and you see on the y-axis how many sources we expect to see within this search radii. So a lot of words, but basically if you look at the red arrow, if you were to take an X-ray source and you say, okay, within 5 arc seconds, which is, given the distribution on the left, assumable positional uncertainty to look within to find the corresponding counterpart, how many Euclid sources would you find? And the answer would be roughly 25, which is a lot, right? Because now you've got a 25-to-1 problem. And given the positional uncertainty, which is large as is, it's pretty ambiguous to guess which is the right counterpart. So more on that in a second. But as for now, with Q1, in case you're not a Euclid member, just a quick rundown of what we're expecting to deal with and sort of the numbers that are involved in this project. The Euclid data release includes 61 roughly square degrees observed in the observational footprint, spread across these 3 subfields. They are primarily chosen for their multi-wavelength coverage. They will eventually make up what is called the Euclid deep field, which means that they will be scanned multiple times to get deeper observations, primarily used for calibration purposes. And these are shown by the mocks on the bottom. And now I can overlay these mocks with pointed observations, or in the case of Rosita, all sky survey scans from the 3 surveys I mentioned briefly. And combined in the table on the left-hand side, you can see that we roughly have 11,000 X-ray sources that we're trying to find counterparts for. You may notice that we have this sort of
gray dotted background in 2 of the 3, whereas in north, you're missing those purely because the visitor footprint doesn't cover the Euclid deep field north. So we only got Folkestone and Chandra. So just something to keep in mind when we're talking about the total numbers. It's not because we're sort of lacking more data in the north, it's just because there's not as much coverage. Okay, so since we're looking for counterparts, the most obvious thing would be to just look at the geometrical matching. So as you would, for example, those of you who use TopCat, you have one catalog, you have a second catalog, you look at the coordinates, you find the source with the, let's say, smaller separation, in this case, the red source here, in this search radius that you predefine. I mean, here I've chosen 1, 2, 3, 4, 5, 6 sources. Imagine these would be 25 now, as I mentioned earlier, it would be pretty crowded. And so, yeah, you start from there. Now, because this is, as just motivated, not very proficient, what we do instead is we employ a code called NWay, which was written by Johannes and Mara. Basically, what you can do is you take the astrometric information, so the geometrical matching I was talking about before, and then you expand that by priors from photometry, meaning if you have, let's say, color space or color magnitude, whatever you're choosing, where you know that your target population, in this case AGN, has specific values that clearly disentangle them from other objects like stars or regular inactive galaxies, you can use the difference of the distributions as a prior that may be pointing towards a more likely match based on its observed quantities. So think of, I mean, I don't have the plot here right now, but like think of the ASEF 90, for example, where you sort of have the WISE W1, W2 selections, and you basically pick a color that is more implicative of having an AGN than a regular galaxy, for example. So what we do is we build these priors by taking a random forest classifier, and we feed it with a training sample of sources from Chandra and Folkestone, for which we, from previous work, know that we have secure counterparts. And so we say, these sources with secure counterparts, because they're AGN, they should be X-ray emitting. You know, we've observed them with X-ray surveys. And then we feed the random forest with features that we get from Euclid, such as, for example, the fluxes, the colors, the signal noise ratios, and so forth. And we let the random forest figure out which of the sources are X-ray emitters, or more likely to be X-ray emitters, and which aren't, basically disentangling AGN from regular galaxies. So if we do this, what we find most noteworthy is that no longer is the closest source geometrically necessarily the true counterpart, right? So it could now switch from red, which would be based on geometry alone, the closest match, to blue, because blue now shows photometric qualities which are much more likely of being coming from an AGN than, for example, from red. And this actually happens for 30% of the cases that we ran this for, meaning that if you flip it around, if you do a geometrical matching alone for any given X-ray survey, or like the ones I just listed, you are likely to, in 30% of the cases, pick the wrong counterpart if you match between different surveys, for example, from X-ray to optical and so forth. Yeah. And so just to motivate this a little bit more, so what I'm showing here on the y-axis is geometrical separation between the Euclid and the X-ray source. And then on the x-axis, I'm showing P-NE. Now, P-NE is an output of NWay. It basically tells you what is the probability that any given X-ray source has a, say, quote unquote, true counterpart in the auxiliary data catalog. And so the higher the value of P-NE, the higher the probability that you actually find a good counterpart for your X-ray source. And so what you're seeing is, because we have sort of like this downward slope, meaning that as you get to obviously lower values in separation, you're increasing your P-NE value. But also, if you look at the color coding, which gives the probability of a source being an X-ray emitter from the random color that we defined, you see that there's a clear color trend, which is probably more dominant than the actual slope of the distribution, telling you that now the choice of your counterpart is much more dominated by its X-ray emittance rather than it just geometrically happened to be close. So yeah, just to basically show you that the random forest is doing a good thing, providing NWay with the necessary information to make more informed choices. Yes, so for all of the X-ray sources that I mentioned, we basically find a counterpart for all of them. There are 5 of them, so you go from 11 291 to 11 286. Yes. which could be driven by edge effects, basically meaning that the X-ray source is somewhere on the border of the observational footprint of Euclid. And so the actual true counterpart is actually not observed by Euclid. It's sort of like on the other side of the board, and so you can pick it up. And none of those which are in Euclid are likely because physically it's not the true counterpart. 90% of those, so roughly 10,000, for those we find unique associations. So just a single counterpart, which is ideally what you want. And for 10%, we find multi-counterpart cases, but these are usually split up between Holzman and also Rosita, just because you have a larger search area. So if you look sufficiently far away, you'll find two sources which may look like an AGN, and therefore they get picked up. But even within this multi-case, we usually have one counterpart which is has much higher P-any values than the rest. So the choices, again, not really obvious. Also, just quickly showing in this Venn diagram, we also have cases where the same counterpart in Euclid is split between different X-ray surveys. So mostly they're assigned to an individual survey, but there are cases where the Venn diagram overlaps, where you have counterparts which are shared between multiple X-ray observations in different surveys, and even 16 cases, they're hard to see in the middle, where all three X-ray surveys observe the same counterpart and assign it to the same X-ray, have three observations of the same potentially X-ray source and assign the same counterpart to that source. Okay, so now you can repeat this entire exercise and shift the Euclid sources at random positions and ask the question, how often do I still find values with P-any values which are sort of based on chance alignments? So just purely by coincidence, you look at an X-ray source and even maybe a different redshifts due to the projection, you're finding a source which is very close along the line of sight. And so probably because of the geometrical alignment, you would say, okay, this source could be the counterpart, maybe not due to its photometry, but it's very, very close. And so the hatched histograms here show you this case for the shifted purple and the sort of salmon colored for the true. And so you can now say, if you take a cut here, roughly where the hatched purple stops, this is sort of the P-any value until potential chance alignments could sort of sneak in. And to properly calibrate your sample, to sort of pick out those sources, ideally, you select anything with a P-any value higher than this value. So you basically calibrate our sample. And so what this looks like is what you can see here on the right-hand side. So if you take now the cumulative histograms of those distributions, we can compute the purity and the completeness for our samples as a function of P-any. So for example, for Chandra sources in the north field of the Euclid deep fields, if you take the point of intersection here, which is basically maximizing for both quantities simultaneously, we get purity and completeness of 91%, which is already pretty high. Now, the cool thing about this is we provide this P-any value in the catalog that we give with the paper, meaning that if you don't care about completeness and you want to have the purest sample possible, you can just choose a P-any value which is much higher. You pick out all of the sources with where you're not as certain, and you retain a more pure sample. But then again, you could go the other way around, and you want to have a complete sample. You just take P-any 0 and you take all of the sources. It's basically up to the user. You have pure freedom as to how to pick and select your sample as you like, basically. Okay, so then we move on to saying, okay, with our counterparts, which we now believe to be true, how many of those do we consider to be galactic, extragalactic? Ideally, you would take a color cut to make this separation, but previous papers, such as, for example, Bisigello 2024, found with the Euclid photometry alone, meaning the photometry from the satellite, you cannot do this sufficiently because basically the feature space doesn't allow you to separate these two populations efficiently. So we know from work from Mara that there exists a feature space, which I'm showing here from Legacy. So the Legacy surveys, the DESI Legacy surveys DR10, where we can find a separation line. So what we do is we match all of our sources to Legacy and then plot them in this feature space, which I'm showing here. And so basically what you see is that everything below here is galactic, so these are probably stars. And then all of this here is extragalactic with the sort of black highest density blob corresponding to where we would expect to see quasars. If we take the separation and I now replot them as extragalactic and galactic in the Euclid color space, we can independently confirm that you see that the distributions are basically at the same place, right? So there is no way you could put a line through this to separate the blue from the orange, meaning that with Euclid photometry alone, you can't sufficiently do this. But again, we want to be able to assign a probability to all of our sources. So we need to go back to the first random forest where we use geometry alone and retrain a second random forest using exactly this training sample now, basically telling or computing a probability for every Euclid source based on its Euclid photometry, whether it is more likely to be extragalactic or galactic. So just quickly flashing the confusion matrix here, but basically the more interesting plot is on the right-hand side, where I'm just showing you the distribution of all of our counterparts as a function of Pigal, which is this probability of being galactic or extragalactic, with 1 being galactic, 0 being extragalactic, because it's basically a binary classifier. And what you can see is that 93% of our sources show up as being extragalactic, so it's probably doing the right thing. And if you color code it by magnitude in the band, you can see that, you know, roughly at 0.5, it flips from having all of the faint sources, all of the faint galactic, extragalactic sources to probably what we see as stars here. Interestingly, because lighter blue is brighter, is brighter than darker blue, then most galactic, according to the random forest, are actually fainter than those which are brighter, which means that probably this is driven by some different populations of stars, depending on where you look on the sky. That's an interesting fact about this plot. Okay, so then we move on to redshifts. From literature, we can find roughly 16% of our sources with spec Z for extragalactic objects. Of course, we would like to have more than 16%, so we have to refer to photo Z. However, the photo Z that come from the pipeline in Euclid at the moment are specifically designed for galaxies or inactive galaxies, because that's effectively what the survey was designed for, meaning that these template photo Z don't account for an AGN contribution. And so what we do instead is we run a code called Pixel, which is image-based photo Z for AGN specifically. And as you can see here from the results for the spec Z sample that we have, so these 16%, also the brighter end, so sources lighter than 21.5 in R-band magnitude, we get outlier fractions of 5%, which is pretty sufficient. And with these results, we get a coverage of 72%, which is obviously much better than 16. So we can work with that. And I'm just showing here briefly on the right-hand side. So the light blue is all of the counterparts. You've got the purple, something so like in terms of coverage, which are the spec Z. Then the golden is anything that doesn't have a spec Z, which we can extend by photo Z. And then so basically green is either photo Z or spec Z, and anything in between. So this area here is where we lack to have redshift coverage. But as you can see on the x-axis, this is a magnitude like 26, 24, 25. So towards the faint end, and at the moment it's pretty hard. I mean, since we use legacy to do the photo Z, where we have a bit more shallow, and then spectroscopic surveys we need to come along in the next couple of years to sort of probe to these faint magnitudes. Okay, moving on. So we then have a look at the X-ray luminosity distribution. This is an example taken from Irisita. As you can see, both for the spec Z, which are the orange points, and for the photo Z, the gray, we find this nice sort of survey arc we would expect to see. With a couple of sources with lower signal-to-noise ratio, which we highlight at the very high end of redshift. So it is yet to investigate if there's a trustworthy or not, but could potentially be interesting sources. If we make a couple of cuts, for example, like we say, okay, the sources have to be, sorry, I just noticed this has to be the other way around, it has to be smaller than 0.5, but basically extragalactic, and the signal-to-noise ratio in X-ray has to be higher than 2 just to kick out some spurious detections. We can actually classify 99 or more than 99% of our sources as being AGN based on literature definitions, for example, in the 2 to 10 kV band, where you have to be above 10 to the 42. So you now might be wondering, why does it say 0.5 to 2 here? It says 0.5 to 2 because we're working with the soft X-ray band from all of our detections, because you want to be able to compare between different surveys. So what we do is we effectively say we're using the 2 to 12 kV band from 4XMM sources because it doesn't have 2 to 10, and we assume same threshold holds, which means anything larger than 10 to the 42, so everything that's orange on this side, is in AGN. And if we now compare this to the 0.5 to 2 kV, means that if you make a cut like this, so around 40, let's say 41, if you're a bit more restrictive, maybe 40 if you're a bit more inclusive, those should be the AGN. We should be able to include all of the sources that in the R band are classified as AGN. Now, these are more than 99%. Now you could ask this last sort of fraction down here, are these low luminosity AGN, are these super soft sources that if you make a go down to 10 to the 39 to include every hard X-ray selected AGN, they have to be extremely soft. And so we need more surveys to have a look at these and maybe get some more X-ray data to see these objects actually are. Yeah, and so then we also look at the hardness ratio and the X-ray luminosity function, as a function of the Y band, so one of the near-infrared bands of Euclid. Without going into too much detail, basically these two sort of diagonal lines are a wedge in which in literature it's been defined that sources that would be classified as AGN would appear. And as you can see, for most of our distributions, we are in this regime. Again, there are a couple of sources which lie below that category, could again be low luminosity AGN. As I said, we need more information to investigate those. At the moment, we're just providing the catalog. We're just having a sneak peek of what is there to have a look at for the moment. But generally speaking, we're sort of within where we would expect to see most of our sources. Yeah, but there'll probably be more papers on this, I expect. Okay, so wrapping up. So with the paper, what are we releasing? So we're releasing all of our counterparts, meaning for every X-ray source, every possible counterpart that we found. So we give basic X-ray information, including the luminosities, you've got the identifier, the coordinates, you've got the redshifts. We provide the probabilities of being an X-ray emitter, being galactic or not. So again, you're free to choose whatever you want, which cuts you want to make. And also P-any, as I said, so you can choose purity completeness of your sample. Yeah, and so you're basically, yeah, as I said, free to choose whatever you want. Yeah, as a little snack takeaway, one of the byproducts of this project is, because I mentioned we have these probabilities for the X-ray emitter and the galactic extragalactic, since we're using only Euclid photometry, I can in principle run these probabilities for all sources in Q1. So not just those that we find counterparts for, so all 30 million. And the distribution of that looks like this plot you can see on the right-hand side. Now, if we focused on this box here, which is highly likely to be X-ray emitting and highly likely to be extragalactic, we find 135,000 sources that have previously been undetected or unobserved in any of the X-ray surveys that we used for this study, which is a lot, right? Probably because we have pointed observations, especially like in EDF and the North Field, which hasn't got any Rosita coverage. And if you start, playing around a bit, so for example, there's going to be a paper on little red dots coming out next week as well. 400 of these sources that have already been matched based on the same Euclid ID to this paper. Those could be potentially interesting objects. But also, so I showed this before on a couple of slides ago. So this is the separation between the extragalactic and the galactic objects. If I match all of these 135,000 objects to legacy, and I repeat the same exercise, we end up with roughly 85,000 sources in this feature space. Again, you have the stars down here. Here's where we would expect to see the quasars. So you can see, I mean, it's probably not great because of the shading, but basically you see this is lighter than, for example, on the edges. So there are some quasars here, which I'm speaking based on legacy photometry that we haven't seen. And there are these objects here, which after a very brief discussion with Mara, we think, I'm not going to be too assertive about this, but this should be maybe clusters or BCGs, or there could be some X-ray emittance coming from the cluster, and then you have the galaxy somewhere in the field of view. And then also these, which should be Seyferts, and they should have a redshift track, which sort of goes up here and then loops back into the quasars, basically. Yeah, and out of anything that's above the stars, so anything on the sort of north part of this panel, we find 83,000 sources. We can work with all of those, and as I said, I'm sure there's going to be a paper about this, and we'll have to do some more thorough investigation. So yeah, I think. Okay. So yeah, this is the reference plot from. Sorry, basically where I'm trying to motivate what I just said. So basically here, these are the kind of hard to see, but these are the clusters. Blue is the Seyferts, and then red is QZOs. And you can see so it corresponds to the same values on the right hand side. Yeah. So I'll stop here. Take any questions if you have any. Thanks.
Questions? Yes, I know.
On slide 16, I was just curious what is causing these features, the stripy features.
Yeah, good question. So because this is a side product and we had an extremely tight timeline in Euclid, I haven't actually had the time to have a look at this yet, but I would presume there's also some artifacts from the random forest algorithms. So you're probably going to have degeneracies where certain cases are going to be more likely than others, which is going to be probably the driver of this distribution. But also physically speaking, I'm sure you'll probably have some objects in the extragalactic sky which share more common features than others. So you're going to have a change in density anyways in this feature space.
Can I add something? In addition to all what you said is the parameters that we are using here are also coming from aperture photometry.
No, this is just tablet photometry.
Not aperture photometry from Euclid here. Okay, then not. Okay, that's fine.
Maybe in the next version.
I want to go back to one of your very first slides where you showed the error distributions, positional error distribution of the different surveys. And unlike the banana shape of Rosetta, the other distributions are a bit counterintuitive in the sense that you do get smaller errors as you go down in flux. And I think this is because, unlike Rosetta, they do not include the systematic error in the positional errors. And I'm wondering if you account for that in some way, because it can increase your search.
So what we did was be unbiased by any selections in the early stages of the analysis. We basically just include anything. And then depending on what we find in sort of the post-processing, you can apply cuts depending on whatever, how limiting you want to be. So if you, for example, fear about detections, you can just remove.
I got a bit confused because did you make any cuts before you started doing all of these analysis and random forest, etc.? Because you mentioned the difference of a galactic and extragalactic and also the X-ray cuts later. So I was wondering if when you start with the whole sample, but using N-way, like trying to find an AGN counterpart, you could actually be looking at, I don't know, X-ray binaries and other sources of point light X-rays, and then maybe associating them with counterparts of AGN.
No, the cuts all start after N-way is complete. So N-way finds all of the counterparts, any X-ray observation that we have, and then, or any point like presumably extragalactic X-ray detection that we have. And then if we start making plots, for example, where we look at sources that we also consider extragalactic, we start making the cuts, for example, on the galactic probability. But at this stage, in the beginning, no, there's no cuts. So yeah, exactly. It could be interesting for people looking at binaries, for example.
Any more questions? Yes, there is Sylvia and then
Hi, William. Very interesting results. My question is about how much do you trust the Euclid photometry? In people in the Quasar work package, we are doing Quasar selection, try to do Quasar selection in Q1, and we found out that Euclid photometry is not really reliable. We tried different operative photometry or temporal fit photometry, etc. We found a lot of artifacts, moving object, diffraction spike, persistence, this kind of thing. So since you were at some point in one of your plot, there was a distribution in the Y Euclid band, and you have sources at 25 of magnitude or something like that. I was wondering how much do you trust the photometry that is basically the base of?
So before I answer that, even if I wouldn't, I couldn't change it. So I'm sort of left with what they have. No, we started also from even using aperture photometry. I guess I can sort of disclose this by now. Well, there were some, let's say, issues, as I'm sure you know, and then there were some issues in the errors. So the path of least resistance was going with the template photometry because we could find at least consistent distributions in those. And but a lot of cases where we would have liked to, for example, used ground-based photometry, and the coverage is inhomogeneous. So if we want to have, for example, random forest applications, and we don't want to be limited by anything that's only in a certain part of sky, it was basically the only way to do it. So, but getting back to your original question, for example, 25 magnitude, yeah. From my understanding, we're producing the catalog, we're putting it out there, and then if people in post-processing figure out that the geometry is all over the place, then we can redo it, right? It's not a problem. We just change the input catalog. But from what we have available right now, these are the results. I'll just leave it at that.
Maureen?
So if I understood correctly from slide 16, when you apply your method, you find like to the, like not to your control sample, but to you find AGNs that are not detected in the X-ray map.
Not yet, actually.
Yes. So these sources are classified as AGNs in other wavelengths?
I didn't check. This is all we did was look at Euclid sources that looked like AGN, and then we said how many of those that look like AGN also would be extragalactic in legacy, and it's these. And now the next step would be to look at if we could find those in different surveys and be more stringent and say these are actually AGN.
That's what I think that it would be very nice.
Right?
Like a new selection that you could apply to find AGNs in the surveys.
Yeah.
That if it is reliable, you don't need.
If I may comment on exactly that bottom plot.
Yes.
For the Rosita Sky survey, we're talking about brighter flux limits, the relative ratio of the quasar peak and this black peak, which is elliptical galaxies, it's much more towards quasar. This may be due to the fact that it's brighter flux limit in part. I kind of suspect that you have still some contaminant galaxies, and this is where the black spot is where galaxies are. So this may still be a bit contaminated.
Oh yeah,
it should. I guess at this level.
Yeah, no. I mean, at the moment we're just being let's say that complete with everything, and then that we can always
fair enough.
be more stringent.
And take a probability of X emitter and 90% instead of 75, you reduce, and then the distribution is going to be weighted. So it's really a choice of the user to pure this kind of sample.
Fantastic. Well, let's thank William again. On Wednesday,